Many natural gas reserves contain nitrogen in concentrations ranging to about 20%. To meet pipeline specifications, the nitrogen level must be reduced to below 4% because the presence of nitrogen lowers the heating value of natural gas. A large majority of nitrogen removal facilities use cryogenic distillation, but such units are economical only for large capacity wells. For smaller reserves, pressure swing adsorption technology has economic benefits, especially because the feed mixtures are available at high pressures. It is desirable to use adsorbents and pressure swing adsorption units that are selective to nitrogen. For most known adsorbents, however, the adsorption selectivity for separation of nitrogen-methane mixtures is in favor of methane due to its higher polarizability. One practical solution is to rely on diffusion selectivities by using microporous materials such as LTA4A zeolite and barium ETS4. ETS stands for Engelhard Titano Silicate. This material is also called CTS-1 Contracted Titano Silicate. And here is a cartoon from the manufacturer which shows the contracted or constricted pores of approximately 3.7 angstrom, which can accommodate nitrogen, because nitrogen is a pencil-like molecule which with a smaller cross-sectional dimension of 3.3 angstrom, whereas methane is severely constricted and is virtually excluded from the pores. This technology is also called molecular gate technology from the process licensors. Details are also available in this publication by Bhadra and Farooq from the National University of Singapore. Further details on nitrogen methane separations are also available on other presentations in my YouTube channel. The primary objective of this presentation is to examine the mixture separation characteristics of barium ETS4 using the Maxwell-Stefan mixture diffusion model. I demonstrate the occurrence of uphill transport of nitrogen and transient overshoots of nitrogen. The origin of the transient overshoot of nitrogen can be traced to thermodynamic coupling effects that emanate from sizable off-diagonal contributions of the matrix of thermodynamic correction factors. I also demonstrate that if thermodynamic coupling effects are neglected, the overshoots are not realized. Finally, I also discuss the possibility of using membrane separation technology using, say, a DDR zeolite membrane that is selective to nitrogen. To begin with, let us examine the experimental data on transient uptake of nitrogen methane mixtures in barium ETS4 as published in this paper by Majumdar. They present two sets of experiments with two different compositions, both at a temperature of 283 degree Kelvin. The transient uptake data is remarkable in that the uptake of nitrogen shows a distinct overshoot in the loadings within the adsorbent BA-ETS4. So the question is, what is the mechanism that allows nitrogen to attain supra-equilibrium loadings during the initial transients before it finally equilibrates to the values that are in equilibrium with the bulk gas mixture surrounding the material. Let's first take up the objective of trying to model the transient overshoots by invoking the theory of the Maxwell-Stefan diffusion for microporous materials. For detailed derivations of the Maxwell-Stefan diffusion equations and explanation of the underlying principles, you may consult my published works. Here I just present the bare essentials of the theory that is required for understanding the transient overshoot phenomena that was reported in the paper by Majumdar. The Maxwell-Stefan diffusion equations properly recognize that the chemical potential gradients are the appropriate driving forces for transport within microporous materials. Here N1 and N2 are the fluxes, and the diffusivities representing molecule wall interactions are D1 and D2. These are the Maxwell-Stefan diffusivities. One of the persuasive advantages of the Maxwell-Stefan diffusion formulation is that these Maxwell-Stefan diffusivities for mixture diffusion can be identified with the diffusivities that can be backed out from unary uptake experiments. Now, the chemical potential gradients can be related to the gradients of the molar loadings within the particle by recognizing that the chemical potential gradients are relatable to the partial fugacities in the bulk vapor mixture. The fugacities in the bulk gas phase are related to the molar loadings via the theory of mixture adsorption, such as the ideal adsorbed solution theory that relies on the use of unary isotherms. Further details of the IAST theory are also available in these publications, and I have a separate presentation on the IAST on my YouTube channel. Now, the chemical potential gradients are relatable to the gradients in the molar loadings by defining a matrix of thermodynamic correction factors that have elements as shown here. For a binary mixture, this is a two-dimensional square matrix, and from applying the theory of mixture adsorption, in general we note that the off-diagonal elements are non-zero, and therefore the chemical potential gradient of any species is a function of both the molar gradients of component 1 and components 2. This leads to the phenomenon of thermodynamic coupling effects. And I wish to demonstrate that thermodynamic coupling effects are the primary drivers for transient overshoots of the more mobile nitrogen guessed within the pores. We summarize the key assumptions that are made in development of the IAST. All the adsorption sites within the microporous crystalline material are equally accessible to each of the guest molecules, and this implies there is a homogeneous distribution of guest adsorbates within the pore landscape. There is no segregation, no congregation, or preferential siting of guest molecules within the pore topology. And the specific surface area that is occupied by each molecule remains unchanged in mixture adsorption. The three basic tenets of the IAST were presented in the previous slide, and if we examine the mechanism by which kinetic separations are realized with barium ETS4 by the size exclusion phenomena, it is obvious that two of the three tenets are not followed in this case of nitrogen methane mixture adsorption in CTS-1. Indeed, in the thesis of Bhadra from the National University of Singapore, there is experimental evidence to demonstrate that the IAST is not applicable. Bhadra also reports experimental measurements of mixture adsorption, and I used the parameters of this mixture adsorption model in the simulations that I will present in the subsequent slides. Indeed, caution is required before applying IAST to mixture adsorption in materials in which one molecule is excluded to practical purposes. I refer to my presentation on my YouTube channel on the IAST for further details on the applicability of IAST and where the IAST theory is not is violated. See also my publication in ACS Omega. So suffice it to say that even though the IAST is not applicable, in my simulations I have used the experimental data on mixture adsorption suitably modeled to examine mixture uptakes and transient breakthroughs. Let us examine transient uptake of a binary mixture of nitrogen, component 1, methane, component 2, at partial pressures 200 kilopascal and 800 kilopascal respectively in the bulk gas mixture, and the temperature is 283 degree Kelvin. We simulate the transient uptake using the Maxwell-Stefan diffusion equations, taking proper account of thermodynamic coupling effects. For these simulations, the data on the Maxwell-Stefan diffusivities D1 and D2 for nitrogen and methane are taken from the publications of Majumdar and Bhadra. We examine the component loadings within the particle for nitrogen and methane. Let's have a look at the animations based on the simulations. Red is nitrogen, blue is methane, and we note a sharp overshoot in the methane loading during the initial transients, and if we wait long enough, the nitrogen loading reduces to a value that is equal to that at the surface, and the loadings at the surface of nitrogen and methane are in equilibrium with the bulk gas mixture. The essential aspect of kinetic separations is that the transient uptake process is terminated during after a time interval during which the component loadings within the particle exceed the values that are in equilibrium with the bulk gas mixture. In other words, the attainment of supra-equilibrium loadings of nitrogen is an essential feature of kinetic separations. For the identical set of conditions as shown in the previous slide, I show animations of the component loading within the particle based on simulations in which thermodynamic coupling effects are ignored and the matrix of thermodynamic correction factors is assumed to be equal to the identity matrix. Let's have a look at the simulation. We note that in this case, there is no overshoot in the nitrogen loading, and both nitrogen and methane approach their equilibrium loadings in a monotonous manner. From the data on the development of the transient loadings within the particle, the spatially averaged component uptakes can be determined from the simulations, and these are plotted in this diagram as a function of the Fourier number. The continuous solid lines are for the model in which the thermodynamic coupling effects are duly accounted for. Red is nitrogen, blue is methane. The dashed lines are the simulations in which thermodynamic coupling effects are ignored, and the matrix of thermodynamic correction factors is taken to be the identity matrix. Gamma ij is the Kronecker delta. When thermodynamic corrections factors are duly accounted for, the nitrogen uptake shows a distinct overshoot, and that overshoot disappears if coupling effects are ignored. Since the objective of kinetic separations is to have the pores loaded with the more mobile component, the inclusion of thermodynamic coupling effects is an essential aspect of the simulations of mixture separations. Now, in this diagram below, I plot the nitrogen uptake versus the methane uptake from the two sets of simulations, both including thermodynamic coupling and the blue one in which thermodynamic coupling effects are ignored. If we include thermodynamic coupling, we note that the equilibration trajectory follows a scenic route to equilibrium, whereas if thermodynamic coupling effects are ignored, the composition trajectory is monotonous. Transient overshoots and equilibration trajectories that follow scenic route to equilibration are essential signatures of kinetic separations. There is also a further aspect that needs to be emphasized, and that is the concept of the kinetic selectivity. Following the works of Majumdar and Bandra, we define the kinetic selectivity as the ratio of the spatially average component uptakes divided by the partial pressures of components 1 and 2, nitrogen and methane, in the bulk gas surrounding the particle. I plot the transient uptake selectivity from the information presented here. This line is the uptake selectivity based on the calculations in which thermodynamic coupling effects are duly accounted for. This line shows the uptake selectivity if thermodynamic coupling effects are ignored. This line is the uptake selectivity based on thermodynamic equilibrium and calculated on the basis of the unary isotherms. The green line are calculations using a kinetic selectivity that is defined by the ratio of the Langmuir constants B1 to B2 and the square root of the diffusivities. This is the kinetic selectivity that is commonly defined in the literature. We note that the Maxwell-Stefan diffusion model corresponds to this value of kinetic selectivity during the early stages of transience for a model in which the thermodynamic coupling effects are ignored. And therefore, this concept of the kinetic selectivity and this formula that is shown here is not of general applicability, and this is a cautionary note to researchers who tend to base their calculations only on this simplified formula. I would suggest that a detailed model using the Maxwell-Stefan diffusion equations is required to determine the kinetic selectivity for such mixture separations. After having examined the transient uptake of nitrogen-methane mixtures within a single particle of barium ETS4, let us examine transient breakthroughs in a fixed bed adsorber. We carry out simulations of the transient breakthroughs using the Maxwell-Stefan diffusion model for intra-particle diffusion, in which thermodynamic factors are duly accounted for. The graph here shows the dimensionless concentrations at the exit plotted as a function of a parameter in which T is the time in seconds, say. Q sub naught is the volumetric flow rate at the inlet, say in units of liters per second, divided by the mass of the adsorbent that is packed into the bed. The blue line represents the dimensionless concentrations of methane, and the red line shows the dimensionless concentration of nitrogen. Methane breaks through earlier than nitrogen, and during this time interval, purified methane can be recovered from the exit of the fixed bed adsorber. The larger the time interval, the larger is the productivity of purified methane. Let's have a look at the animation showing the development of the concentrations of methane, shown in blue, and nitrogen, shown in red. These concentration fronts, as they traverse the column, are much slower for nitrogen because nitrogen is preferentially taken up within the pores due to diffusion selectivities. Nitrogen elutes the bed later than methane. An alternative to the use of PSA technology for nitrogen methane separations is to use membrane technologies, and I show an example here of nitrogen methane separations using a DDR membrane that offers permeation selectivities in favor of the more mobile nitrogen. DDR consists of cages that have a volume of 278 cubic angstroms, and each cage is separated from adjacent cage by narrow 8-ring windows that have an aperture that is 3.65 angstrom in this direction and 4.4 angstrom in this direction. nitrogen, being a pencil-like molecule, can diffuse from one cage to the adjacent cage through the windows because the hopping occurs lengthwise across the windows. This is demonstrated in the animations in my presentation on diffusion and DDR zeolite. Methane, on the other hand, that has a molecular dimension of approximately 3.7 angstrom, is severely restrained and cannot jump from one cage to the adjacent cage as frequently as nitrogen. The permeation selectivity is largely dictated by the diffusion selectivity that favors nitrogen. And I show here simulations of the permeation fluxes plotted against the time. This is a transient permeation. And these calculations are performed using the Maxwell-Stefan diffusion equations. We note that the permeation flux for nitrogen shows a pronounced overshoot in the fluxes before it reaches its steady state value that is higher than that of methane. So during the initial transients, only nitrogen permeates through the membrane. The calculations are based on the models that are described in the literature. See my papers that are referred to here. Now this DDR membrane could be a potential candidate for use in nitrogen removal from natural gas. Let's have a look at how a DDR membrane unit would look like. The company called NGK Insulators in Japan offer membrane modules shown here that consists of circular tubes. The inner wall of the tubes are coated with a thin layer of DDR zeolite, and this layer is typically about 20 micrometers thick, and this is the substrate. The DDR zeolite allows selective transport of nitrogen across the membrane, and such units can be used for nitrogen removal from natural gas, perhaps in conjunction with a PSA unit. The takeaways from this presentation are summarized in the slide. Transient overshoots and serpentine equilibration trajectories in composition space are signatures of kinetic separations of nitrogen-methane mixtures using barium ETS4. Our simulations have established the occurrence of uphill transport of nitrogen within the pores of barium ETS4. An important feature of uphill transport is that it follows the scenic route. And I quote the poet William Wordsworth, who has underscored the benefits of following the scenic route, because it opens up new vistas